We're going to define the incidence matrix for a graph and for a digraph. We're going to define the adjacency matrix. We're going to define the distance matrix. And we're going to use this distance matrix to help us define the diameter and radius of a graph. The incidence matrix is an n by m matrix, where n is the number of vertices in the graph and m is the number of edges. So if you have a graph with 9 vertices and 15 edges, then your incidence matrix is going to be a 9 by 15. So for our first example, we have a graph that has 6 vertices. So we've labeled the rows 1 through 6 that correspond to the vertices. And we have 5 edges, and we've labeled the columns that correspond to the edges. Now notice that row 1, that means we're looking at vertex 1, and vertex 1 is incident to the edges A and C. So we have 1 under A and a 1 under C, and zeros elsewhere. For a second example, if we look at vertex label 2, vertex label 2 is incident to edges A and B. So we look at row 2, and we have a 1 under A and a 1 under B, and zeros elsewhere. So this is how we construct the incidence matrix for a graph. Proposition 2.5.1 says the sum of the entries in any row is the degree of the corresponding vertex. That makes sense because it counts actually the number of times that vertex is incident to an edge. And proposition 2.5.2 says the sum of the entries in any column is equal to 2. Again, that makes sense because given any edge, which is what you're looking at per column, given any edge, you have exactly 2 vertices that define that edge. Let's find another example. So we'll return to this graph, and we can see by the labels that we have 6 vertices. So we'll have 6 rows. How many edges does this graph have? We can add the degrees. So we have 1, 2, 3, 4, 5 vertices, each of degree 4. So there's 20 plus 2 more. So we have the sum of the degrees is 22. So by the handshaking lemma, half of that's 11. We have 11 edges. So 6 vertices and 11 edges will give us a 6 by 11 matrix. So if we construct our matrix, if we look at, say, vertex 1, it is not incident to edge A, so that's why we have a 0 there. Or if we do it by column, if we look at edge A, it's incident to vertices 3 and 6. And so we'll have a 1 by 3, and we'll have a 1 placed in the 6th row, and those will be the only 2 ones. What will be column B? Let's look at edge B. Edge B is incident to 1 and to vertex 3. So we should have a 1 in the 1st row and a 1 in the 3rd row, and zeros elsewhere. And again, we notice that if we sum, we should always get 2. We should always get exactly 2 ones in any column. So I believe you can construct the rest of this matrix. Do you agree with the third column? There are 2 1s, and C, edge C, is incident to vertex 1 and vertex 4. Now let's talk about the incidence matrix for a digraph. The incidence matrix for a digraph, it's no longer true that the sum of any column is equal to 2. However, if you look at our example, you'll see the sum of any column is always 0. So that is because if you have a directed edge, you have a head and a tail, a beginning and an ending. So we will place either a 1 or a negative 1. So if we look at E1, edge 1, it's leaving C and going to A. So we put a -1 by C and a +1 by A. Let's look at E2. It's leaving B and going to C. So we'll put a -1, like it's taking away from B, and going to C, a +1. Just one more. How about E3? It's leaving A and going to B. So it's a -1 in the A row and a +1 in the B. Our next topic is the adjacency matrix. The adjacency matrix is a square matrix where each row in each column corresponds to a vertex. Notice that every vertex, and if we don't have loops, which in simple graphs we don't have loops, so no vertex is adjacent to itself. So that means we have zeros down the diagonal for a simple graph. Vertex 1 is only adjacent to vertex 2, so in the first row we have a 1 in the second column, and that's the only place. Vertex 2, on the other hand, is adjacent to both 1 and 3, so we have a 1 in the first column and a 1 in the third column. Since we don't have direction, we have symmetry. If 1 is adjacent to 2, then 2 is adjacent to 1. So you'll notice that this is a symmetric matrix if your graph is not directed. If you sum each row, then again you obtain the degree of the vertex. If we allow multiple edges, we can take the same adjacency matrix, and let's say that we allow multiple edges. So we'll add another edge, we'll draw in an edge from 4 to 7. That means vertex 4 is adjacent to vertex 7 2 times. So if we look in the 4th row, 7th column, we should replace that one with a 2. You can think rather the ones as counting than the number of edges. Instead of saying if it's adjacent, we'll put a 1, we could say 1 is the number of edges between the 2 vertices. The distance matrix is also a square matrix where each row and each column represents a vertex. But now the entry is based on distance. Recall the distance between any 2 vertices is the length of the shortest path. So in general, there might be many paths between 2 vertices, but the length of the shortest one is the distance between the 2 vertices. So again, we have zeros down the diagonal because the distance from any vertex to itself is 0. Let's look at the first row of our example. vertex 1, it's a distance of 1 from vertex 2. So we have a 1 in position 1, 2. Going across that first row, we see the next distance is 2, and the next distance is 3. However, we have 2 4s. And why is that? Well, the distance from 1 to vertex 5 is 4, and the distance from vertex 1 to vertex 7 is also 4. So because of that fork, we find that we can go from 1 to 5 by the same distance we go to 1 to 7, and it's 4 in both cases. And then the distance from 1 to 6 and the distance from 1 to 8 is 5 in both cases. So our first row ends with 4, 4, and then 5, 5. Notice that if we go to, say, the third row, that would be vertex 3. There isn't a 5 in the third row, because vertex 3 has a more central location. Vertex 3 can go to 8 along a path of length 3, and it can reach all the other vertices within 3. So if you look at the third row, the highest value is 3. Now, the diameter of the graph was defined in our book back in exercise. It's much easier to use the distance matrix to talk about the diameter of a graph, so that's what we're going to do. The formula for the diameter of a graph is given below, where the diameter is the maximum, where this maximum is taken all over all pairs x and y in the vertex set, and it's the maximum distance between any pair of vertices. So if you already have the distance matrix, then finding the maximum distance is simply looking at the distance matrix and finding its largest entry. Since, for example, that's 5, then the diameter of this graph is just 5. The radius is a little bit more complicated. The radius formula is given below, and the radius is the minimum over all pairs of vertices of the maximum for every vertex. So what does that mean? We can't say the radius is simply the smallest value in the distance matrix, because that's always 0. Zero is on the diagonal. But rather, what we want to say, it is the least distance in the sense that, well, let's just back up. Let's look at the first row. Notice that the largest value is 5. So we will have to go 5 in order to go from 1 to any other vertex, or at least 5. So let's find the maximum of each row. So the maximum in each row is now given. And as we discussed earlier, the maximum of the third row and the fourth row is just 3. Now that we have the maximum of each row, we take the minimum of all the maximums. That's what our definition is telling us. So if we take the minimum of the maximums for the radius, then in the column under maximum, our minimum is 3. This graph has a radius of 3. That means really that there is a vertex in the graph that you can go from to any other vertex in the graph by no more than 3. So we've defined the incidence matrix, the adjacency matrix, the distance matrix, and use that distance matrix to help us calculate the diameter and the radius. The diameter and radius definitions are found on page 38 And the rest of this material is in your book on pages 74 through 77.